Just gonna copy this right quick. So we've talked about alkylation. We talked about halogenation, and we've talked about with the alkylation, some potential pitfalls with that. So today we're going to talk about Friedel-Crafts acylation. And let me rearrange these pages right quick because I need to move this. So that Friedel-Crafts problem is one problem, and then we got three other examples that we're gonna work through now here after we finish the acylation part, and then we'll talk about directing effects, and we'll be done with this section. All right, so acylation is exactly what it says, what an acyl group is. So an acyl group right is here, right? So we're adding in a carbonyl to the ring, right? We're adding a carbon. You can see right here on the ring, you can see the carbonyl substituent right here, right? So with that acylation, the mechanism is relatively the same. It's just the initial step of activation that's different, right? So with the Friedel-Crafts acylation, you're going to start with an acid chloride. That's my one of my start materials. Right. So that is C. All right, it's a very reactive functional group. It's similar, it reacts similar to like an ester or carboxylic acid, but it's much more reactive than both of those. All right, so we're going to add in, we're going to use this acid chloride, right, to add in the acyl group onto the ring. All right, so it's the chloride part that's going to get activated. All right, so in step one, that's where we activate. Let me go change colors right quick. In step one, we're going to activate the carbonyl. So that's that. It's going to form a coordinate covalent bond with aluminum trichloride, just like before. All right, so you end up with this. Right, and then you're actually going to lose the chloride. Right, so the intermediate that you get from that, that's going to be that reacts with the ring, will look like this. So you got a positive charge on that carbonyl carbon. And now that aluminum tetrachloride is negative. So this is going to be your reactive species, right? That's what the ring is going to attack. All right, any questions about that first part? So in step 2, what's going to happen? Is something new going to happen? Something extraordinary that we haven't seen before?
No.
No.
Oh,
Right. The purpose of me doing this with this level of redundancy is to prove a point that once you understand what happens initially, you can apply that same information to multiple examples, right? So the only difference in all 3 of these reactions that we've studied is the first step, how your electrophile gets activated. Other than that, everything else is the same. So in the second step, I want to bring my activated electrophile down here, right? Ring is going to attack it. Now I have my iridium ion intermediate. What happens with the iridium ion? What's the next thing that has to happen?
the hydrogen has to, or will it move over to the,
No, it's not going to migrate because remember, there's a hydrogen over there already.
So we need to reestablish, like, make it fully conjugated again.
Yeah. So we do that through an elimination, right?
Yeah.
So that negatively charged aluminum is going to provide that pair of electrons. Let me fix this. It's going to provide that pair of electrons to remove that proton and put that double bond back to reestablish aromaticity, right? So that's your third step. And now you have this, right? Plus your catalyst regenerated, plus HCl. The HCl comes from right here. Once you pull off that hydrogen, right? That aluminum tetrachloride is unstable, so that's how your catalyst gets regenerated. One of the chlorines from the aluminum tetrachloride is furnishing a pair of electrons to that proton, right? And then regenerating the catalyst at the same time.
I have a question.
Mm-hmm.
Okay, so, well, can you like zoom out?
Mm-hmm.
Okay, so for like step 1,
Mm-hmm.
so step 1, we're just focusing on the substituent, basically.
Yeah, we're activating. This is the electrophile activation step. Because we have to prepare the electrophile for the ring to attack it.
Okay.
All right, and then step 2 is nucleophilic attack of the ring. And then step 3 is to reestablish aromaticity. Right, same 3 steps. And you have to reestablish that aromaticity because that's a really like a highly stable system, the aromatic system. So you don't want to break that up. All right, any other questions? All right, let's work through some of these examples. And I'm going to leave the mechanism part for you to do. All right. What is, so it says, again, predicted products. That's different from proposal mechanism. If I ask you to predict the products, that means I'm asking you to show me what the result is of these two reactants coming together and doing a reaction. If I ask you to propose a mechanism, I'm asking you how that happens. So the first one says predict the products of the following reactions. All right. So what type of reaction is that first reaction? Right, I got an acid chloride. In the presence of an aromatic ring and aluminum trichloride as the catalyst. What type of reaction is that?
Is it Frito Crafts? That's
Go ahead. You're on the right track. It's an acylation, isn't it?
yes.
Mhm. What I'm adding, what I'm doing with this reaction, that's the reaction we just did, actually. What I'm doing with that reaction is I'm adding this whole thing to the ring, right? And with that ring, all of the carbons are equally susceptible. So it doesn't matter in this particular case where you put it. All right, so what's the product? We know that the aromatic ring is going to be a product.
Would you lose the chlorine?
Yes, yeah. The chlorine is not going to be a part of the product. So I'm just going to add in this group just like that. Right. If I'm doing an acylation, just like we showed up top, you start with an aromatic ring, right? An acid chloride and an aluminum catalyst. And whatever is attached to that acid chloride ends up on the ring, right? Sans the chloride. So you don't put that on there. Or chlorine, sorry.
And then it would be like the catalyst again, and then plus
Yeah,
HCl.
Yep. Yes. All right. What about the second one? What reaction is that?
Halogenation. Halogenation.
Halogenation. Good. What's the result of that?
The BR is going to be attached to the ring.
Yes, only one, right?
Yes.
So the result of this reaction is here. Right, you're always going to get the catalyst regenerated. You don't consume a catalyst, it's not a reagent. Right, so that's the outcome of that reaction. All right. All right, let's see if we can do, somebody can help us with the last one. What type of reaction is that? And what's the outcome? What am I adding to the ring? All of these are nucleophilic aromatic, I'm sorry, electrophilic aromatic substitution. So what am I adding to the ring in this case?
Is it the substituent attached to the CO?
Yeah, I'm adding this group, right? That's exactly right. So that's all, when you have to predict a product of one of these types of reactions, that's what you're looking for. What am I going to add, right? So in this case, this is a Friedel-Crafts alkylation. It's on a tertiary carbon. Right, so what's the product from that?
That group is going to be attached to the ring except the CO.
Is that right? And
Yes.
then plus. Right, you always regenerate the catalyst. Any questions about that? All right, let's go to the next section, and we're gonna come back to those reactions actually, because we're gonna talk about, we'll talk about the nomenclature part last. But let's do this. Since we're already talking about the reactions, I don't want to stop doing that for nomenclature, which I hate. So we're going to talk now about directing effects. And this pertains specifically to doing a reaction on an aromatic ring that's substituted, right? So before we talk about donating and accepting and all that stuff, let's talk about resonance on an aromatic system. All right, so here, let's say if I have a phenol. All right. How many resonance, as a matter of fact, let's say we have the phenol anion. Let's start here. All right. How many, can I do resonance with that?
Yes.
You see this pattern right here, this allylic anion pattern. So I can do resonance here and here. Now I got a negative charge there, electrons here, and electrons here. Everybody okay with that?
Yes.
What about here? Do you see that same allylic pattern here? and do resonance again. Wise man called me in class. All right, is that right?
Yes.
All right. Can I do it again? See the pattern? So this is here. Make sure I got the ring. So now I got a pair of electrons here, here, here. Everybody okay with that?
Yes, sir.
All right. So what you notice in the resonance form is that the position that's immediately adjacent to that. So we started out right here, right? The ring is substituted with this oxygen, all right? And so here, right next door to that oxygen, that position has a pair of electrons. Everybody agree with that? And then if you look right here, there's also a pair of electrons. I need to fix that arrow. It looks like a fish hook. There's also a pair of electrons here on that carbon. Is that right? The
Yeah.
ones on the other side over here are identical, right? It's not going to change anything if I stick an electrophile there. So that's the same as the first one. It's adjacent, it's right next door. All right, so let's say if we started counting from the substituent, that this is position 1, right? What a carbon where it is position. So that's 1, that's 2, that's 3, and that's 4. Are we okay with that?
Yes.
All right, so for a mono-substituted benzene ring, that second position right here, this is again 1, 2, 3, and 4. We call that second position the ortho position. Only if the ring is mono-substituted, and we're getting ready to add something else to it to make it di-substituted. All right, so that's ortho. And then over here, this is again 1, 2, 3, 4. All right, so this 4 position is what we call the para position. Right? So oxygen attached to that ring is it's a donor. It's an electron donor. Do you agree with that? The fact that it could push electrons into the ring? It didn't
Yes.
it didn't pull electrons out of the ring, did it?
No.
No, it pushed electrons into the ring. So it's a donor. It can furnish a pair of electrons. Right? So if you have a donor attached to your ring, right? The 2 positions that get activated are the ortho and the para. So donors right? So the donors are going to activate the ortho and the para positions. The reason that's important is because if you're doing electrophilic aromatic substitution, the electrophile desires to go wherever the electrons are. So if there are electrons at the ortho position and the para position, that's where anything you add to this ring that has a donor already attached to it, it's going to end up at either ortho or para, right? So electrophiles will only add at those two positions. So prior to the reaction, right? An electrophile is only going to add to those two spots if there's a donor on the ring prior to the reaction, right? Because again, we're in each one of the cases we've looked at, the ring is the nucleophile and whatever we're adding in is the electrophile, be it a halogen or an alkyl group or an acyl group. All of those are electrophiles being added to the ring. Right? So now let's think about if we put an acceptor on the ring. So let's look at a different case. So I'm going to take a ring, an aromatic ring, and I'm going to put a carbonyl out here. Right? And I just want to make a point with the aromatic system. If it has a carbonyl, which is an acceptor. Right, and we think in terms of resonance, we could do this. Agree, disagree? Is that right? If I shift that pi bond outside the ring, that carbon right here is going to become positive. Is that right? Because I broke a bond to it.
Yes.
Yes, sir.
Right. So if I wanted to add an electrophile to that site, could I do it? Remember, I'm adding an electrophile, which is a lover of electrons. If there's a positive charge at that site, can I add an electrophile there?
Not like at the booty.
No. No, I can't add an electrophile because the electrophile is looking for electrons. If a carbon is positive, that means it's devoid of electrons, right? Or it doesn't have enough electrons. And it definitely doesn't have any it can give away. So I cannot add an electrophile there. What position is that? If I look at where the substituent is prior to the reaction. What position is that?
You mean like
Relative to the
carbon number?
carbonyl. Mhm.
Is it carbon number 6?
You must be counting all the way around. That's okay. We're gonna count 1, 2, 3, 4. So it would be 6 if I count it from the opposite direction. I agree with that. But in this case, we're gonna call it 2. But we can count either direction.
Okay.
Mhm. So that second carbon, what do we call that up here?
Ortho.
Ortho. It's the ortho site. Would you say that so at the ortho site, there are no electrons with an acceptor on the ring, right? So we could say that the ortho is deactivated. Right? That's deactivated. Right? It's deactivated. What that means is I can't add an electron there. I mean, I can't add an electrophile there. All right. I can do another resonance form too. I can do this one because I got the same allylic pattern. It's just an allylic cation now. So I can do this. I got a plus charge down here. Right. And let's number it again. That's 1, 2, 3, 4. What site is that compared to where the carbonyl is attached?
Para.
Para. Good. So this is para. And since it's positive, can I add an electrophile to that site?
No.
So the para position is also deactivated. Right? And then if we did another resonance form where we take this pair of electrons and move them here, you'll see that the other ortho site is going to be deactivated. So now this is here. That's positive. And that. And here. All right. So now that would be 6. Who was that said 6 initially?
Me.
I can't see you. You got to say your name.
Quinetta.
Okay. So this is also ortho. That's also deactivated. Come on, Russell. All right. Now, what do you notice about all of these where the ortho site might be deactivated or the parasite is deactivated? Let's see. 1, 2, 3. Where can we find electrons in those resonance forms?
The oxygen.
Okay, besides that, in the ring, only in the ring. That's what we're looking. Are there some electrons at 3? There's a power bond there, right? That can be used. Is that right?
Yes,
Same thing over here. Got a power bond right there. Is that right? And then even over here, you see that there's a power bond present. So that third site, if there's a substituent already on the ring, that third site, we call it the meta site. Right, so on a ring that's mono-substituted, it has 3 locations where you can do a reaction: the ortho, the meta, and the para. So here at site 3, that's what we call meta. And that, if there's an acceptor on the ring already prior to the reaction, that's the site where the reaction is going to take place. So the meta is what we call activated. Meta is activated. We're going to steal this. The difference is that it has to be an acceptor that's attached to the ring. So for rings that have acceptors attached that can pull electrons out of the ring, then those rings get substituted at the meta position, at the 3 position. And you always start counting from the carbon where your substituent is, right? So the meta position is, if where your substituent is 1, then at carbon 3, based relative to that, that's what we call meta, right? So here, that's my meta site, right? Questions? Any questions about that? So I think at this point, we need to make sure we understand the difference in a donor and an acceptor. So a donor is an electron donor. It can give electrons away. So up here, I don't have to rewrite this because it's actually up here. Okay. Maybe I didn't. Oh, that's okay. I can write it out. I'll give you some examples of donors and some examples of acceptors, because every donor is not a resonance donor and every acceptor is not a resonance acceptor. Sometimes it's by induction as well, right? So let me write that down here. Right, of course, any heteroatom with electrons on it, like oxygen, sulfur, nitrogen, and then let me not do that because I don't want to have to have a charge on it. Any heteroatom that has electrons can be a donor, right? It can donate electrons back into the ring, right? Alkyl groups are also donors, right? So alkyl groups, heteroatoms, halogens, even though traditionally we thought about halogens as acceptors because of their electronegativity. When you put a halogen on an aromatic ring, it's going to be a donor, right? So these are ortho, para directed. What that means is that anytime you have a donor on the ring, it's going to direct the electrophile to the ortho site or to the parasite when you get ready to do the reaction, like up here, right? I have a methoxy group on the ring. When I get ready to brominate that ring, that methoxy is going to tell bromine you can only go ortho, which is right here. See that? 1, 2, 3, 4, right? You can only go to position 2 or position 4. All right, so this is ortho. And then this is para, right? And that's strictly based on the fact that the methoxy group is a donor. Right? If I have an acceptor on the ring, let me give you some examples of those, and then we'll be done. Right? Of course, you have resonance acceptors like carbonyls. That can be any carbonyl. It can be an ester, it can be a ketone, aldehyde, it doesn't matter. Nitriles, like that. Nitro groups, all of those are considered acceptors, resonance acceptors. Right? And then as far as inductive acceptors, if you have electronegative groups attached, something like a CF3, right? This would be by induction. But these are all what we call meta directives. Right? So you got donors that are orthopara directors, and then acceptors, which are meta directives. And donation and accepting can be either through resonance or through induction. All right, any questions about anything? We're gonna work through a few of these on Friday. A few problems that have like different donors and acceptors on it. We'll just add it to this worksheet. So it won't be a part of this PDF, but the problems that we do, you can write them in. All right, any questions about anything?
I have a question.
Go ahead.
Are we gonna do the last problem on the sheet together, or is that one on your own too?
Which one is that?
It says if a Frieda-Krauss alkylation is carried out in a primary alkyl halide, sometimes unexpected products are formed.
Oh,
I
we
don't
did that
know that
on
one.
Monday.
Oh, I missed. Okay,
Oh, we did it Monday.
okay, thank you.
Mhm. All right, any other questions?
Can you go back to the,
The last page?
no, it was actually one of the first problems we did when we did the acid chloride halogenation and then the alkylation.
Right here?
Down a little bit. Yeah, that's good. Thank you.
Mhm. All right, other questions? Gordon.